So let's do an example involving variance for a continuous random variable. Consider this random variable x, whose PDF is 1 over x to the 3 halves on the interval 1 to 4. Looks like this. We're going to do three things. We're going to find the expected value in the variance of that random variable. We're going to find the value of little x. So the probability x takes a value smaller than little x is 75%, 0.75. That's called the 75th percentile of the random variable. So that means that I want the value where 75% of the area is on the left and 25% is on the right. And then in part C, what's the probability x takes a value within 2 standard deviations of its mean? So after we do part A, we'll know the standard deviation and the mean, because the expected value, that's also called the mean. The variance, we'll take the square root and get the standard deviation, and then we'll be able to actually figure this out. And this is leading up to Chebyshev's inequality, which gives us a bound on what this probability can be without actually knowing the details of the way our random variable is distributed, knowing only the expected value and the variance, but that's next time. So let's get started. Find the expected value. Okay. So for a continuous random variable, the expected value you get by integrating x times the PDF. And now this integral goes over the whole real line, but it's 0 except on the interval 1 to 4. So we only have to integrate from 1 to 4 because the rest contributes nothing. And so we do this integral, integrate from 1 to 4, x times our PDF up here, 1 over x to the 3 halves, dx. And if you work that out, what's it going to be? Let's see. You're going to get x to the 1/2 in the denominator, so you're going to end up with x to the minus 1/2, right? Just exponent laws there. Okay, and so we will do that integral, do an antiderivative here. What do I have to take the derivative of to get this? Well, I guess x to the 1/2, right? So when I take the derivative, the power goes down by 1. And when I take the derivative, a 1/2 will come out in front, and I want that to go away. So I'll put the 2, 1 to 4. Okay. So now when I plug everything in, I get 2 times square root of 4 minus 2 times square root of 1, which is 2 times 2 minus 2 times 1, which is 2. Okay, so there you go. The expected value of our random variable is 2. Right here, sanity check. Okay, that makes sense as kind of the balance point of this PDF, right? So now the variance. Next thing. So for the variance, you could use the definition, which would be, I would integrate from 1 to 4 x minus the expected value we just found squared times the PDF. But we also know that, remember that we don't have to do this. We could also use the fact that the variance is equal to the expected value of x squared minus the expected value of x squared. We proved that for discrete random variables, and it's still true for continuous random variables. So I'm going to do this instead, and the reason why is because when I go to do this integral, this is going to expand out and give me lots of terms, which means I'm going to have to, it's still going to not be a difficult integral, but it's going to be more work because I'm going to basically have some kind of a, won't be a quadratic because there's powers of x in here that are going to mess things up, but I'm going to have 3 terms, all with different powers. Whereas in here, I'm just going to have one term. So this is going to be easier. So let's do the expected value of x squared. All right. And by the law of the unconscious statistician, the expected value of a thing, I'm going to integrate that thing, with little x here, times the PDF of x. So that's applying the law of the unconscious statistician. It says the expected value of a function of x is what you get when you integrate that function of x times the PDF of x. Okay, good. So this time we're going to integrate from 1 to 4 x squared times 1 over x to the 3 halves dx, which is going to give, when you do the exponent laws, I guess 1/2. Now I'll do an antiderivative. What do I have to take the derivative of to get x to the 1/2? Well, it would be x to the 3 halves. But then I want to put a 2/3 here, right? So that when I take the derivative, the 3 halves comes down and cancels with the 2/3. And I just end up with x to the 1/2. Evaluate from 1 to 4. We get 2/3 times, what's 4 to the power 3 halves? Well, the square root of 4 is 2. 2 cubed is 8. And then the 1, it's just going to give me a 1. Times 1, which is equal to, what do I get here? 8 times 2 is 16, minus 2, 14/3, looks like. All right. And so that was the expected value of x squared. And so now we're going to get the variance by doing that thing minus the expected value of x squared. So here we go. So the variance of x is equal to the expected value of x squared, just to remind you, I'll write it again, minus the expected value of x all squared. So we get 14/3 minus, what was the expected value? What was the average, the mean? We found that before. It was 2, right? It was 2. Okay, so minus 2 squared. Good, which is 14/3 minus 2 is 2 squared is 4. How many thirds? That's 12/3, right? So we end up with 2/3. All right, so our variance is 2/3. And done part A. Expected value is 2, and the variance is 2/3. Great. So what's next? Part B. Find the value of little x, this number on the axis up here, where the area to the left, the probability x is less than that number, is 75%. And the area to the right is 25. So somewhere in here, there's going to be a number where the area on the left is 75 and the area on the right is 25. Let's find it. So how do we do that? Well, what I'm going to do is I'm going to remember that, this is for part B. Yeah, well, I'll just keep going on the next sheet. I'm going to remember that the probability that x lands in any interval, in particular, the probability it's less than little x, is going to be the integral from, in this case, 1. I can start at 1 because I know 1 is the smallest value that has it's non-zero in the PDF here. I'm going to start at 1, and I'm going to go up to some indeterminate number, and I'm going to set that equal to 75%. So I'm going to integrate from 1 to something. In this case, the probability x is less than or equal to little x is the integral from 1 to little x of my PDF. Now there's a problem here though, which is that these x's mean different things. This little x here is a number on the x-axis I'm searching for, whereas this little x in here, this is a variable I'm going to integrate out. And so you might remember this happening in Cal 2. I'm going to replace one of these with a dummy variable. Sorry, this is the dummy. I'm going to replace one of these with a different letter so that I don't confuse the names of these two things. One is the number that I'm integrating up to, and the other one is the actual variable x on the x-axis. So I'm gonna, in this case, I guess I'll replace this one with, let's say, little t. Could do either one. And that way there's no confusing here. I'm trying to find this value t, where this integral comes out to be 75%. So I want this probability to come out to be 75%. So I'm going to integrate from 1 up to t. I'm going to integrate my PDF, which was 1 over x to the 3 halves, right? Yeah, 3 halves dx. And so I just have to do this and solve for t, and I should be good. Right, because just to, again, make sure you're okay with this difference of the names between variables. So I'm thinking of x, really it's the name for the variable on this axis. And it can be a large range of values, the range I'm integrating over. Whereas this upper limit, I want to find this single value. So t is going to be some number in here, I don't know where. And I'm going to evaluate the integral up to there. And then I'm going to set that equal to 75%. And hopefully that'll give me a value for t. Okay, good. So here we go. Yeah, this integral, once again, it's going to be an easy integral. Because we're going to write this as 1 to t of, what's in here? X to the minus 3 halves, right? So, yeah, what do I have to take the derivative of to get minus 3 halves? Well, it had to come from minus 1 half, because the power rule tells me when I take the derivative, the power goes down by 1. And then I guess I want a minus 2 in front to cancel with the minus 1 half that comes down. So minus 2, little x to the minus 1 half. Take the derivative of this, that, yes, will give me a 1, and it goes down by 1. Okay, great. Evaluate from 1 to t. So in the end, I end up with this little equation here. Minus 2 over square root t, right? Minus 1 half is like dividing by the square root of that thing. Minus, then I plug in the 1. And that just gives me a 1 here. Minus 2. Okay. Great. So this is a plus 2. I'm going to move it over there. That'll be a minus 2. So it should be minus 1.25, I think, equals minus 2 over root t. And they're both negative. That's okay. Move the t over, the root t over. So 1.25 root t equals 2. Right? I'm doing two things at once. Multiply both sides by negative 1, then multiply both sides by root t. And then I get root t equals, what's 0.25? 1.25 is 5 quarters. And 2 is 8 quarters. So I got 8 quarters divided by 5 quarters, 8 fifths. And then I square both sides. And I end up with, what is this? Square both sides, so we end up with 64 over 25, right? Let me square. Cool. So 64 over 25, what is that? That's like somewhere between 2 and 3, right? 64 over 25. Yeah, I don't have my computer. But anyway, that's what it is, somewhere between 2 and 3. And so we figured out that 64 over 25, that's somewhere between 2 and 3 here. That's the 75th percentile. So if you were to put 64 over 25 on this axis and measure the area on the left, you would get 0.75, and the area on the right would be 0.25. So it's called the 75th percentile of the distribution. Okay. Good, now finally, the last part. What is the probability x takes a value within 2 standard deviations of its mean? All right. So remember that the mean, what was the mean? We figured out it was 2, and the variance was 2/3. So if we take the expected value, the mean, plus 2 standard deviations. I use the symbol sigma, x for the standard deviation of x. Then that's going to give me 2 plus 2. What are the standard deviations? The variance was 2/3, so that means the standard deviation is going to be square root of 2/3. And do the expected value minus 2 standard deviations. That's going to be 2 minus 2 times the standard deviation. Okay, and we'll figure out what these are. Let's do this. Sorry about this, but let me quickly do those calculations. Here. 2 plus 2 times the square root of 2/3. It's about 3.63, and 2 minus 2 times square root of 2/3 is about 0.367. All right. Okay, so we're going to find the probability that our random variable takes a value between 0.367 and 3.63. Well, look here. 0.367. Well, it's always bigger than 0.367 because it's always bigger than 1. 3.63, somewhere in here. Okay, so this is going to be a big probability. Most of the time, a random variable is in this range, right? Between 3.63 and 4, it happens pretty rarely. So notice that we're going to integrate from here to here, but I can just integrate from 1 to 3.63 because the region between 0.367 and 1, it's not going to contribute any probability. Great, so the answer to our question that we're looking for. The probability x is within 2 standard deviations of its mean. You could write it like this: mu x minus 2 sigma x, mu x plus 2 sigma x. So remember these symbols, mu x, that's just the mean of x, the same as the expected value of x. And sigma of x is the standard deviation, which is the square root of the variance. It's going to be the integral from, and I guess to be perfectly honest, I'll put a little approximate here, right? Because I'm going to use 3.63 up here. From 1 to 3.63. Remembering that the reason I can start at 1 is because a random variable always takes a value bigger than or equal to 1. So to be bigger than 0.367 is the same as being bigger than 1 in our particular case here. And so I'm going to integrate the PDF on there. 1 over x to the 3/2 dx. Great. And that one I'll just leave to you, but I want just to point out that we could do this question, right? Once you know the mean and the variance, you know the standard deviation. What's the probability x takes a value within 2 standard deviations of its mean? Well, I just figure out, go 2 standard deviations above the mean. Oh, whoops, these were swapped around, weren't they? Sorry about that. Go 2 standard deviations down from the mean, you get here. Goes to 2 standard deviations up from the mean, you get here. And then I'm going to integrate my PDF, making sure to cover that region. And then I'll get a number here for the probability. I think this should be pretty big number, pretty close to 1.